Okay, thanks a lot, Dimitri, for this introduction. So I will talk about this work I did about theta function and optimal lattices for a grid cell model. So it will be about, traveling through time. So before traveling through space, I would like to travel a bit through time, because in 2014, we have this very nice workshop about optimal point configuration here in the same room. And it was my first talk as a researcher abroad. I was PhD student, and today is my first talk abroad as a permanent position in France. So I think it's a nice thing. No, I don't do that for okay, thank you. Anyway, so now my talk is over. No, okay, so I continue. So the goal of this talk is to present a mathematical biology model. It's very unusual for me. Usually I present physics thing, but today that will be only mathematical biology. And the goal is to show the existence of a kind of inner GPS in the brain of mammals, so in particular of rats, where the grids from lattices map the position of an animal in space. Right? And of course, as usual, when you do that in applied mathematics, one looks for a mathematical justification of this phenomenon. And so there will be some modeling, analysis, optimal lattices, and numerics. And I will explain some, remind you some results about optimal lattices for theta function at the same time. And the reference is this paper I wrote. It was published in Science Journal of Applied Mathematics. Okay, so what are grid cells? So just don't worry, a grid cell is simply a neuron, right? So that every time you will see grid cell will need just a neuron. And the story started with these three persons who got the Nobel Prize in 2014. So Edward Moser, Maybrit Moser, and John O'Keefe. So you know, if they are very happy, that's the kind of face you should have when you get the Nobel Prize, right? Of course. And they got the Nobel Prize for their discovery of cells, so neurons that constitute a positioning system in the brain. So O'Keefe started this research in 1971, and Moser, so husband and wife, they continued that after that and got some first result in 2005. So where are these neurons in particular in the brain? They are in this very like pink violet area, which is called the entorhinal cortex, right? And we all have that in this room and outside, of course. And the function in the entorhinal cortex includes being a widespread network hub for memory, olfaction, navigation, which I will explain today, and the perception of time. So what is exactly the experiment? The experiment is extremely nice. You have a rat, and so he's moving in a 2D closed environment without any obstacle, so pretty big with respect to the size of the rat. And an electrode is implanted, poor rat, in this entorhinal cortex. In one, exactly to measure the activity of one particular neuron, right, which is called a grid cell. And the rat is moving, and each time this neuron fires, okay, the position of the rat is marked, for example, this head. And what you observe in that case is that the neuronal activity is concentrated on some zones that are yellow here and red here, which are called firing fields, the fields where the neurons are firing, and they are forming a triangular lattice. So that's extremely nice, extremely strange at the same time. So that's also that's a true picture, right? I didn't do anything here. That's a triangular lattice formed by neuron firing field, right? Here, so you have this firing field, and you see that when you take a center of this field, you can get a perfect triangular lattice. So of course, as usual, it's natural phenomena, so it's not perfect, but the idea behind that is that there is maybe something perfect. So what I will call lattice here, that will be a discrete set of this form, as usual, right? Generated by D vectors in RD, independent vectors. And the triangular lattice is this object in red that we know, which is basically up to the scaling here, generated by 1, 0, and 1 half square root of 3 over 2, right? And this is just the one with unit density, just for this. Through the medial entorhinal cortex, actually, through this cortex, you have a change of grid density. That's interesting. So if you do like a slicing of the entorhinal cortex, you will have different density for the triangular lattice, but you still observe it, right, at different scale. So that's quite nice. And on the other hand, you have, of course, many neurons, okay, in this entorhinal cortex, and they are like, you know, firing at different positions. So all these grids, they are like shifted or dilated or rotated, right? And so that's the fact that all these things are like doing that together. That map the space, right? The 2D space. And there's something called the modular organization. So a grid module, what it is a set of grid cells with the same grid density. So the density is fixed, but we've shifted and rotated face. Okay, so that's quite normal. So if you fix the densities, then you can play a bit with other parameters. And of course, they should recall you some other physical things. So linked to the crystallization conjecture. That are like abricos of lattices, Bose-Einstein condensates, and Lennard-Jones energy, right? So this triangular lattice, you can find it in many places. As we all know, and I think Thomas spoke about that last week. And yeah, so I mean, that's connected to the Ginzburg-Landau theory, some Gaussian model, renormalized energy, etc., etc. But here I'm not going to speak about that. That's my usual topic, but not today. Okay, so now we are going to do some mathematical modeling, right? So be careful, I mean, we should stay in science, but not in science fiction. So we should do something quite relevant. You have a lot of literature about this problem of grid cell, right? I will not do the list here, but so many people try to explain with some tools, mathematical tools, statistics, and so on. Why do we have this triangular lattice, right? This grid, this thing. And there is this paper by Matthias Stemmler and Hertz of 2015, and they use information theory and packing problem. Okay, that's this paper I had it on my desk for, I think, 5 years. And I was thinking about reading it one day, and then I read it and I said, okay, I can do something with that. Making a model which is a bit more, let's say, flexible, a bit more complicated. But basically, if you want to read all the details of the of what I'm going to explain, it's also very nicely explained in this paper. So it's mostly in 2D. I will speak at the end about 3D grid cells, right? For us in a 3D environment, or for animals in 3D environment, but very briefly. Okay, so the approach I chosen here, and which is the same of Matisse and his collaborator, is this information theory approach with the Kramer-Rao bound. So it's not necessarily something we are doing all here, but anyway, I would just be very quick for the modeling. So we are considering n, so small n neurons, okay, with the same grid. So the density is fixed. The grid is the same for everyone, right, for all the neurons, and with grid cell modules. Okay, so for each neurons, you have n shifted faces. So, well, for one neuron, you can shift n times in different direction. I will show you the vectors after that. And that's the same for all the neurons. Okay? So we are doing statistics. So we are taking a certain number of neurons, and we'll do some things with that. So the true position of the rat, because it's a rat here, it's x, and it's encoded by your brain as x hat. So there is something, an information between your eyes or your senses and your brain, which gives you x hat. And you want to minimize the encoding error, which is given by the expectation value with respect to some probability that I will show you after, of the distance between x and x hat. It's a usual thing in statistics. And a good estimator of this minimum from the Kramer-Rao bound, actually, it's the inverse of the trace of what? Of the Fisher information. So there is something called Fisher information that you had to use here. I have to admit that I didn't know all these things before, but and what I will do also, I will aggregate the phases around each point. So, you know, we have all these phases, all these points, discrete phases shifted. But to make it a bit easier, I will aggregate everything on a certain compact set. So I will take just the empirical measure, and I will take a limit, and I will at the end have a measure on the firing thing sigma. Right? So all these small balls that you saw was like just with some points. But here that will be a perfect ball. Don't worry, everything will be nice and everything will be easy. So when I will take the limit as n goes to infinity, I will get a functional of a lattice L. So that important thing here is that I will consider only lattices. So the point configuration I'm considering are only lattices, right? And I will optimize this Fisher information with respect to lattices. Okay? And things which is a bit different from what we are used to do is that here the idea is to maximize, okay, because you know the Gaussian estimator of the minimum is 1 over trace. So you want the minimal value here, you have to maximize the trace. And so the idea will be to maximize this functional among lattices. Okay. Good. So now I'm speaking a bit more about the modeling itself, but I will be a bit fast, right? Because it's, I mean, not boring, but at least it's something that you can find the literature easily. So you just assume that all the neurons, these n neurons, are independent. So the probability that they fire at K1, K2, so we have the neuron 1, 2, 3, etc., n, and the probability that the first neuron fire K1 times, the second K2 times, the third K3 times, etc., is a product of each probability to fire K1 times, K2 times. Okay, so I can decorrelate everything like that. Okay. And everything will be on a time interval, but it does not matter. It's really, think T as infinity if you want, it doesn't matter. Okay, so we have this probability, and that will be the product of smaller probability, let's say. Okay, now what I take is my connection is stable. Okay, the firing statistics. So for each neuron, the firing statistic will follow a Poisson distribution. So I choose a Poisson distribution, and you can choose whatever you want. Again, right? I mean, it's not you choose it like that. And the parameter, which is the average value, is called here omega ix. Okay, that's the average firing number. Sorry. Also called turning curve of the neuron number I at position X. Right? So that's average value of the average firing number, so number of time. And always in this intervals. Okay, so you can write each probability I showed you before like that. Okay, and now I choose, let's say, some assumption for the average firing number, and I say that this average firing number is L periodic with respect to a certain lattice L. Right? So if you are around one lattice, you will have this certain distribution of firing numbers, let's say, but that will be the same everywhere on the lattice. Right? But the lattice can move. That's important. Otherwise, it's so that's what I wrote here. So this firing number will be in the form of a certain energy, okay, of a shifted, I mean, that's the interaction between X and the lattice, right? So that's exactly what we are used to see. And F will be decreasing very fast at infinity, as usual, and L is the lattice, right? But don't worry, F will be a Gaussian at the end of the day. Okay, but you can choose whatever you want. Why not? Okay. And now I add the modular organization. So for each neuron, I have N, capital N, shifted version, okay, of the tuning curve. Okay, but I'm only considering shifted version, not rotated, just shifted. So each neuron is associated with N over things like that, and you can shift all the time. Okay, and so the vectors for the shifting are called yj, right? And the probability, okay, for one shift, so one part of the module, is given by exactly what I explained before. Okay, so the thing is that this exponential does not depend on I, because they're the same for all I. That's what I say. I say it's periodic like that, and that's what remains the product of these quantities, right? Okay, and this object is, of course, the shift of the lattice, right? So that's energy given by the sum for P on the lattice of F of P plus X plus YJ square. So you shift again. But it doesn't really matter, because at the end of the day, I will take X equal to 0, because I will just try to find the good estimator for the origin. Okay? So it doesn't really matter here, but just to give, for completeness, I can give something a bit general like that. Okay, last thing about statistics, I use a Kramer-Rao bound for my error. Okay, so I know that the covariance is bounded by the inverse of J, which is J is the Fisher information. It's a matrix. This matrix is given by this integral over all the possible firing here. Okay, in terms of the probability. Okay, so for in our module here, which is very nice, G is diagonal, and actually G is extremely simple. And that's why we can only care about the inverse of the trace, right? Okay, we know that the trace of the inverse is not the inverse of the trace, but in certain cases it is, and it is in this case. Right? So now for each entries of this Fisher information, you can write it as a sum. Like, okay, so the Fisher information, the total Fisher information is the sum of the Fisher information rest for each part of the module. Okay. And now you can compute that actually. So you can compute that because you know what is the Fisher information for a Poisson distribution. Okay. So that you take your textbook, you open it at a good page, and you say, okay, I know it, and just recopy it. It's not more difficult than that. Okay, you can of course prove it, but it's fine. So at the end of the day, what you get for the trace of this matrix is n times, so small n, it's the number of neurons, the sum for all the j, so all the different vectors, yj, of what? Of the norm, so this is an Euclidean norm, of the gradient of my tuning curve, so this energy which is shifted, divided by this energy itself. So I wrote it again with EF, so my energy with respect to F. Okay, so that's a horrible thing. Very horrible thing. If you want to minimize that, I will show you in a few moments that it's extremely difficult, and that's a really complicated thing. So that's why you simplify a bit, and then you average each phases around each point, each lattice point, right? So you take the empirical measure with respect to this shift, and you make, I mean, you choose a measure mu such that this empirical measure converges to mu. So you can take a probability measure if you want. I mean, it is a probability measure actually. So, okay. Very well. So now you can take the limit. So everything passes pretty nicely to the limit. There is no problem because everything is continuous in a certain compact set, blah, blah, blah. So there is no problem at all for the analysis here. And so you compute the Fisher information, so the limiting Fisher information per neuron. Okay, so you divide by n, and you take the limit as n goes to infinity of the trace divided by n. Right? And if you do that, you obtain an integral. Okay, against the measure mu. And now what you do is you simplify a bit because here, you know, you have two parameters. You have y you integrate with respect to y, and there is this x which shifted the rest, so it's not very nice. So you take x equal to 0. Right? So what you want to do is you want to maximize the decoding resolution. That's the name of this object actually. The decoding resolution of the ice brain information at x equal to 0. So now you already want to know how to reconstruct the signal you have at the center of the plane. Okay, so our energy is written like this integral, and that you can write again as the norm of the gradient of the square root of this, which is not super nice, but at least we can do something with that. Okay, so the mathematical problem is the following. So I choose f to be this exponential such that f of r squared is a Gaussian. I take pi because we know that for the theta function, that's a good number to choose. And now given nu, and therefore given the firing field sigma, so okay, where the neuron are firing, we want to maximize this functional, okay? So that's so here I wrote the lattice theta function. So more precisely, the translated lattice theta function. That's just the Gaussian energy for a lattice translated by a vector y. Right? So, but that's exactly the energy you want to maximize. So that's not easy. I have to tell you that yeah, you have many energies, and this one is extremely complicated. But you want to minimize among lattices. You can show that you have a certain scaling formula, and from this scaling formula, you know that there is no minimizer if you don't fix the density. So that's the usual thing with this problem. So you have to fix the density to be 1, for example. You fix the density equal to 1, and then you minimize among lattices of density 1. Yeah, right? So you maximize the energy among these. So that's our mathematical problem. These mathematical problems involve this theta function, and that's why I want to talk about optimal lattice for theta functions and for packing, for example. So Dimitri last week spoke about energy minimization and so on. So it could be related to that and to the previous talks we had, especially yesterday, for example. Okay, that's Einstein's desk, actually. So that's the state of the art. So once you read all these books and all these papers, you are ready to attack the problem. Okay, so lattices and packing, we know, right? I mean, I think we all know that. So I put a picture of Hales and the Kepler conjecture such that you have this FCC or HCP lattice here, and you can see the nice triangular lattice here as a slice. Okay. In 3D, because I will speak about 3D things at the end. So there is this simple cubic lattice, the body centered cubic lattice and the face centered cubic lattice. Okay. So this one, the middle is called D3 star, and this one is a dual of it, so it's D3. Okay, just for the notation, but don't worry, I will repeat it again. And we know that, so in dimension 2, that's the triangular lattice, which is the optimal best packing. And dimension 8 and 24, the best packing, we know it are the Gaussian lattice E8 and the Leech lattice lambda 24. So that's we know. And in the original paper of Matisse et al. And his collaborator, actually they did something about packing. So if you want to read it, it's interesting, but because at some point, what I call this turning curve with this Gaussian, everything is simplified there, and at the end of the day, what you want to maximize is the density of the packing. That's why for them, it is a triangular lattice. That's why for them, it is the FCC lattice and all these lattices, right? I mentioned 8 and 24. So for the theta function, we also discussed that. We heard some nice talks yesterday about it, and maybe you know all these things. So for the Gaussian energy among lattices, so now I'm just among lattices, we know from Montgomery that the triangular lattice is the optimal minimizer. So I'm speaking just about minimizer. Cohn and Kumar, okay, they conjecture that you have universal optimality in the very general sense for periodic configuration. In dimension 3, we know that there is no universal optimizer, so meaning that the BCC and the FCC lattice plays these roles for alpha smaller than 1 and larger than 1. Okay, so that's a problem in dimension 3. You cannot find this use this theta function very nicely. But you have only a local minimality result, that thing that we got with Mircea-Petrake and things that I also prove, but the idea was from Enola in particular in my work. So, but you can show that it's not for any alpha. So for depends on the density, you don't have always the same local minimality result. So, and of course, we know that E8 and the Leech lattice are unique minimizer among periodic structures. So you have in dimension 8 and 24 universal optimality. Amazing result that we got recently. What about the translated theta function? Because it's a building block of our energy. So for the translated theta function, meaning that this Gaussian energy, so that's the energy between Z, so a point in our D, and a lattice L. Right? So you want, so there is two problems. The first problem is, can we find the minimizer of that? So you have a lattice and you look for, so you fix the lattice and you look for one point which minimizes this interaction. So for that, we know that if L is orthorhombic, meaning that if the unit cell is cuboid, right? So you just follow the orthogonal direction. The center of the unit cell is a unique minimizer, and there is only one. Right? And that's something we showed with Mircea in 2017. And for the triangular lattice, we know that the barycenters of triangles are minimizer. Okay? So that's a bit related to what Nate Tempest told us yesterday. And yeah, okay, so that's the first problem. Okay, the second problem is something that we showed with Markus Vollhuber and Stefan Steinerberger very recently, is to maximize the minimum value that you found just before. Right? Okay. And that's a polarization problem, as Sergei told us the very first day of the conference, but for lattices, not for any kind of point configurations. And we show with Markus and Stefan that we show that the triangular lattice is a unique maximizer, okay, for this problem. So the triangular lattice is the solution of the polarization problem at fixed density. That will deserve a full talk, right? I'm not talking about that, but that's something interesting. And you have many consequences in time frequency analysis for charge lattices and so on. So it's on archive. Yes.
Oh, I'm a bit confused. So here Z is fixed. Then A2 is a unique minimizer for a fixed Z.
Here, so the problem one, Z moves and L is fixed. So the lattice is fixed, so you fix the lattice and you bring with this.
But in the theorem, the last theorem, here Z is fixed and you are maximizing over lattices.
So you start to minimize. So Z is fixed in the sense that Z depends on the lattice. Z depends on the minimum. It should reach a minimum.
For every lattice, you first find the shift that gives you the minimum value of the function, and then you
exactly.
And then you maximize that.
Yeah, but in our case, we managed to do it without finding the minimum.
Just to find it. Exactly.
Okay, so that's what you understand. We have to understand here is that it's extremely difficult to minimize the discrete energy that I described before, because it's already something with the gradient of a translated theta function divided by a translated theta function. So it's clearly a monster that you want to minimize, to maximize here. And of course, it's a very difficult, even Yj are very nicely put in this very nice deep holes of middle point and so on. Okay, so that's already difficult. And just to show you, you just have to look at this paper by Luo and Wei, and they prove some result of minimization for the sum of the theta function and the translated theta function. And if you look at it, you can really see the difficulty just with one shift here. Right, it's extremely difficult to show what the minimizer is among lattices and among points. Right? And so this paper is about two-component Bose-Einstein condensate and the Ohlmüller conjecture. So if that's another nice open problem, it's still open because it's not totally solved, but I mean 90% of the proof is there. And you can also see the Nate Tampa's talk because it's also a bit related to that and show you the difficulty of showing it. And there is another object I want to talk about before giving you the result we had. That's the soft lattice theta function, meaning that instead of looking at one lattice, right, and an interaction of point, you put a mass at each lattice point and you look at the interaction you get here and what is a minimizer, right? So you replace the point by masses. And actually radially symmetric masses with a measure mu, right? So you take something nice, because if it's not nice, it's another story. And with Antknüpfer, we show that if the firing fields or if the masses are sufficiently low scaled around the point, right, but there is still some mass, since you have the minimality of the triangular lattice in dimension 2 for theta, you will have the same for this guy, right? And that's the same is true if you take a measure which is written in terms of completely monotone function. Same kind of. Okay, and the same is true if you consider local minimality result, okay, in any dimension. So everything stays true. That's the same proof. So if it's true for the point, it's true for the masses, but not so big masses. I put in remark too what the completely monotone function means, but of course we saw it yesterday, so I don't want to talk about too much. And now I want to state in the 10 last minutes what are the optimality results we get for the grid cell problem, okay, for our problem. Okay, so I recall the problem here. So minimizing this object among unit density lattices, right? And this object, we saw it before, that's the translated theta function. So this is a general configuration of firing field. Okay, this gray thing, and this is the one you want to be a maximizer, right? The triangular lattice, exactly what you want. Okay, so a result you can get is an asymptotic result in the sense that for small alpha and small lambda, you have non-optimality of the triangular lattice. Okay? Basically, so what you have to take here is that you have to take mu radially symmetric. So I take mu radially symmetric, and I take a ball as sigma. Okay, that's an extremely easy thing because otherwise it's a bit difficult. And the first result you get is that if you fix any lattice in dimension 2, there will be an alpha naught and a lambda naught, strictly positive, such that for alpha smaller than alpha naught and lambda smaller than lambda naught, the energy of your lattice L that you have chosen randomly is larger than the energy for the triangular lattice. Meaning that the triangular lattice cannot be a minimizer for alpha small and lambda small. Okay. The point 1, okay, it stays true independently of lambda, okay, if your measure is completely monotone, okay, in the sense that it's as before. Okay, so it's not, of course, it's not like a surprise because I used the result we got for masses in this case. So for alpha and lambda very small, you can show that your functional can be written in terms of the functional you have for the lattice, soft lattice theta function. And then instead of having a maximum, you have a minimum, basically. That's the idea. So since we are going in two opposite directions, that's why you have non-optimality. And it's even worse because if alpha and lambda are very, very small, the function does not have any minimizer. So meaning that actually, so what you have to think about is that lambda small means that the ball are very small. So you rescale everything. Lambda is a rescaling of the ball. Right? And alpha small means that the Gaussian is more and more flat. Right? So in that case, that just means that if you have balls with basically, I don't know, I mean, just kind of uniform distribution of firing thing inside, right? It's very bad because actually it's better to be a minimizer than a maximizer because you are still almost like points. And for points, we know that it's more a minimizer than a maximizer. That's a full philosophy of this proof. Okay, I didn't want to show too many technical stuff. And in dimension 3, the two first points, so these points are, the two first one are, they hold for lattices in an open neighborhood of the body centroid cubic lattice. So for alpha small, actually, we know that the body centroid cubic lattice is locally minimal. That's why it works. Okay, that's just okay. So sigma and alpha cannot be simultaneously small. That's we know. Second reason you can get is a stability result. So if you play with lambda and you assume that you play with lambda, so the measure and sigma are dilated with lambda, and at the same time the lattice move with lambda. So everything move with lambda. You rescale everything. And you can show that you are a critical point of this energy. So with respect to of this energy, sorry, for all lambda in an open interval. So if lambda is in an open interval and you have a critical point in this energy for this energy, therefore, and if it's if and only if actually, the open interval is actually all the positive value, the positive distance, and the lattice is necessarily either the triangular, square, cubic, FCC, and BCC lattice. You have no other choice. So it's an interesting thing because we saw that you have a lot of different scaling. Of course, we don't know if the scaling are in an open interval in the sense continuous, right? It doesn't make really sense because there is a finite number of neurons, but a big one. But it's something that just tells you that these lattices are the only one that could be stable in that sense. Right? It does not show anything in terms of optimality, but it's a good clue that this lattice should be the good one. Right? And to show that, you use some Delon-Rishkoff and Gruber's arguments for with two designs, stories, and that's why you have this list of lattices. Right? Because you use only that. So that's only among lattices, of course, not only. Okay, now I'll just show you some numerical investigation I did just to show you that actually the model is quite good for the problem. So now, until the end of the talk, I will suppose that the measure is uniform. Okay, that's a uniform probability measure on a ball. Okay, so very easy thing. And I will take alpha equal to pi over 10. It's just a number I choose. You can change alpha. It's not very important because with the scaling argument, you can always find something like that. So that's the profile, okay, you get for F. And so in dimension 2, you can show that the triangular lattice is a unique maximum. So show means observe, right? That's just numerics of the functional for R equal to 0, 1, 0, 2, 0, 3, blah, blah, blah. And when you take the packing radius. Okay? So when the balls are touching each other, it's still true. Of course, you can do whatever you want here. I've chosen just these numbers, but you can choose whatever you want. In particular, you can just choose the experimental value. So in general, it seems that from the experimental value, the diameter divided by the backing radius should be 0.3, right? So there is a good thing which fits with experiments. And for this one, it works also. That's one example. Of course, you can do whatever you want because you can play with alpha. So you can always choose your alpha such that your R fits with the maximality of the triangular lattice. And what you can also see with these parameters is that for R sufficiently large, so larger than 0.59, there is no minimizer. And actually, the triangular lattice is a unique, there is no maximizer, sorry, but the triangular lattice is a unique minimum, the minimizer of the function. So it's R is too big, the balls are overlapping, it's bad. So that's one example of things you can do. So you parameterize your lattices in the elliptic domain, and this point corresponds to the triangular lattice. This one corresponds to the square lattice, and then you see that the maximum, so the white part, is for the triangular lattice. It's a usual thing that you do when you work with lattices. And in dimension 3, you can show the same kind of thing, but it's of course more difficult. So I just compare the BCC, FCC, and Z3, right? And for R smaller than 0.55, you see that the FCC lattice is the best. And it seems to be true for R less than this packing radius of the FCC lattice. Just an observation which fits with what these people from neurobiology did. Right? This paper I told you, Matisse and I. But actually, 6 months ago, or even less, there was a paper from this person, okay, these researchers, and they did things in 3D for the flying bat. They took a bat and they put the same electrode in this entorhinal cortex. And the bat is moving, and what they see for the firing things is that there is a characteristic distance between nearest neighbors. So the firing things, there is a distance between them, the same everywhere, but it's not a lattice. Okay. So there is a local order, but there is no global order. That's what it is observed. So it's observed that you have more of this object here than the one. This thing, and the good model seems for them to be the Lennard-Jones potential with temperature. So they compare with this thing, and they found that it should be comparable, and it's a good model, which is quite interesting and quite puzzling. And so I will finish with some open problems in the sense that we don't have a rigorous proof of what I'm just show you, right? It's because it's a kind of a monster, it's a kind of a difficult object. Another idea would be to compare the boundary effect. And so if you do that, that's an experiment showing that on the boundary of the area where the rat is moving, you have some deformation, of course. So the lattice is not really triangular on the boundary, but more like that. Right? And you can also change the form of sigma. And that would be, for example, an ellipse, and that would change also the lattice, which is the maximum. That's maybe interesting. And the last thing you can do is to choose another F, which is non-Gaussian, and to show, for example, I don't know. I mean, there are many questions here you can do, like universal optimality result or this kind of thing for this problem, right? So I just show you that because I think it's a nice new problem that we could try to tackle and to attack and at least to find some interesting related problem. So I've finished. So thanks a lot for your attention. And if you want more information, you can visit the Chris page I did, which